Alright, I'm guessing most of you have played bowling at least once in your life. Maybe you're terrible at it like me, maybe you're actually really good. In fact, the best players among you can throw the ball at speeds of around 22 miles per hour. Of course, by the time it hits the pins, it has already lost some speed because of air resistance and friction against the lane. Now, imagine a bowling ball slamming straight into the earth at 99% of the speed of light. What would happen? Would the effects be devastating? And if so, how devastating? Today, we're answering the following question. What if a bowling ball hit the Earth at 99% of the speed of light? And we're doing it in 360 seconds. First of all, is there any kind of matter capable of moving that fast? Or at least getting close? What kind of matter can come closest to the speed of light? Not exactly, but there is one that can almost get there. Plasma. That makes up most of the matter in the universe. It's a state of matter, just like solid, liquid, or gas, and most of you have probably already seen it in certain lamps. The kind with a glass sphere and a glowing core. Its main characteristic is that it always exists at a very high temperature, and it's made up of electrons separated from their nuclei. And yes, you can find quite a lot of plasma in space. But plasma doesn't move at a very high speed unless something accelerates it. And what better way to shake things up than black holes? That's right, black holes absorb every form of matter, including plasma and even light. Of course, that absorption doesn't happen all at once. It works more like a siphon, like water draining through the hole in a bathtub. Except here, you have to think in terms of millions of miles. And every now and then, as this happens, jets of plasma are launched outward. That's when plasma reaches its maximum speed. In some cases, close to 99.9% of the speed of light. This phenomenon is called a blazar. As for a bowling ball, here's what it looks like. It's a little over 8 inches in diameter, and it can weigh anywhere from 6 to 16 pounds. Let's split the difference and go with a weight of about 8.4 pounds. In space, our bowling ball wouldn't have to deal with the same friction it does on a bowling lane, but to reach 99% of the speed of light, it would need to move just a little faster than it does on the lane. Yes, it would need to be thrown 8,480 times harder than usual. 148 3,000 miles per second. In other words, at that speed, our bowling ball would take about 1/3 of a millisecond to cross the roughly 60 miles of Earth's atmosphere. It would have absolutely no time to burn up the way a meteorite of the same size would. So how do we calculate the impact power of an object like that? Quite simply by calculating its kinetic energy, meaning the energy it has because it is moving. The result is expressed in joules. A joule is, first of all, a unit used to measure energy, but in our case, we'll use it to express the force exerted by an object, the bowling ball, over a distance of 1 meter in the direction that same force is pushing it. Still with me? Good. So what formula do we use for that? Unfortunately, classical formulas won't help us here because at those speeds we have to use the theory of relativity. You've heard of E equals mc squared, Einstein's famous formula. That's the one we need. Well, almost. We also need to include the Lorentz factor, gamma, which comes from the formula 1 over square root of 1 minus v squared over c squared, where v is the speed of object and c is the speed of light.
The numbers! What are they saying?
I'll spare you the details of the calculation. If you want to try it yourself, feel free to pause the video. The result comes to 2090 petajoules, or 2 billion joules. To put that into perspective, the impact will release about as much energy as 10 Tsar bombas, the most powerful bomb ever detonated. A single one of those equals 4,000 Hiroshimas, and to get that kind of power using plain old TNT, you would need enough explosives to form a cube of 671 meters on each side. That's twice the height of the Eiffel Tower. You would also need no fewer than 1.2 billion high-speed trains, each weighing 444 tons and traveling at 320 kilometers per hour to match the impact force of our bowling ball. In terms of celestial bodies, if a meteorite traveling at around 20 kilometers per second were to have the same impact power as our bowling ball, and if we assume it has the same density as a chondrite, a common type of meteorite, it would need a mass of 10,450,000 tons. Its diameter would be around 177 meters, or more than 6 basketball courts. But let's get back to our bowling ball. With that kind of power, the effects would obviously be devastating. But what about the explosion itself? The easiest way to visualize it is with an impact simulator. Remember that our bowling ball would have the same effect as an explosion of about 500,000 kilotons of TNT. Let's assume the bowling ball hits right in the middle of Ile-de-la-Cité, in the very heart of Paris. The entire city and its inner suburbs would be swallowed by a massive ball of plasma with a temperature twice that of the sun's surface. Everything inside that zone would be literally vaporized. The explosion would spread across 9 departments and buildings would be blown apart within a 56-kilometer radius, about 35 miles of the impact point. The heat would be so intense that within 150 kilometers, about 93 miles, people could suffer third-degree burns and likely die. So, if you're in Orléans, Amiens, Rouen, or even splashing around the beaches of Dieppe, you're done for, literally. But that's not all, because the blast wave from the explosion could shatter windows as far as 2,800 kilometers away, about 1,740 miles. In other words, if you're on the east coast of Greenland, you might see windows shatter. As for the crater, it would be around 750 meters wide, a little more than 8 times the height of the Statue of Liberty, pedestal included. And that's without even mentioning the magnitude 8.5 earthquake and the tsunamis that would come with it. In other words, you definitely wouldn't want to be anywhere nearby if a bowling ball ever hit the Earth at 99% of the speed of light. Still, compared with the Chicxulub asteroid, the most famous one of all, the one believed to have wiped out the dinosaurs with its 15-kilometer diameter, our bowling ball would look pretty small. But how would humanity react if such a catastrophe really happened? That's for everyone to decide.